Greetings of the day to all of you. Welcome to lecture number 40 of our course on power quality problems and solutions. In today's lecture and probably in the next lecture, we are going to discuss a very interesting topic on modern AC to DC power converters, which we also call as improved power quality converters. I will write here improved power quality AC to DC converters. AC to DC converters. And in short, we write them as IPQCs. I for improved, P for power, Q for quality, and C for converter. Improved power quality converters or improved power quality AC to DC converters. The other names given to these converters are, if you search the literature, you read the research literature, research papers, journal papers, conference papers, and some very modern good books on power electronics, you may find different names given to these modern AC to DC power converters. They are very famously known as improved power quality converters, IPQCs, but they are known by other names also in the literature. Other names are high power factor converters. High power factor converters. That is HPFCs. Other name is power factor correction converters. Power factor correction converters. That is PFCs. The other name is switched mode converters. Switched mode AC to DC converters. The other name given to them in the literature is pulse width modulated converters. Pulse width modulated, that is PWM converters or PWM rectifiers. Okay, so they are given different names in the literature. Why they are called improved power quality AC to DC converters? Because these AC to DC converters, unlike conventional AC to DC converters, thyristor based and diode based AC to DC converters, unlike those converters, they always maintain a very good quality of power both at the input side as well as on the output side. On the input side, they result in least distortion in the currents, almost negligible distortion in the currents. In other words, they draw almost sinusoidal currents from the source, whereas you have seen the conventional AC to DC converters, rectifiers and phase controlled converters, they draw highly distorted current from the source. But these improved power quality converters or high power factor converters or power factor correction converters or switched mode AC to DC converters or PWM converters, they draw nearly sinusoidal current from the source. And not only that, the current is also in phase with the source voltage, making power factor unity, which means that they do not draw any reactive power from the source. Whereas in case of AC to DC converters, conventional or traditional AC to DC converters, especially phase controlled converters, those converters are very notorious for drawing large amounts of reactive powers from the source, even if the load on the DC side is purely resistive. But depending upon the delay angle or firing angle, if you are operating your phase controlled converter at large value of firing angle or large value of delay angle, they draw large reactive power from the source. But these improved power quality AC to DC converters are known not to draw any reactive power from the source. They draw only active power from the source, thus maintaining the supply or source power factor at unity. Similarly, on the output side also, they maintain a very high quality of power. That means the output voltage, which is the DC voltage, is almost ripple free or it has very reduced ripples. It's called reduced rippled output voltage, and it is highly regulated. Okay. Why they are called high power factor converters? Again, the reason being same, they maintain nearly unity power factor on the input side, on the AC side. Again, it is because of almost unity power factor on the input side that they are also called power factor correction converters. And why they are called switch mode AC to DC converters? Because in these AC to DC converters, you are using modern self-commutated power semiconductor devices like power transistor, power MOSFET, IGBT or GTO or IGCT, and you are using them in the switch mode at very high switching frequency. Okay. And why they are called pulse width modulated or PWM rectifiers? Because they use pulse width modulation technique as the modulation algorithm is PWM algorithm. Okay, which makes them high power factor converters or power factor correction converters or improved power quality AC to DC converters. And before discussing various types of these AC to DC converters, you have to understand that what is the problem with conventional AC to DC converters? What is the serious problem or serious drawbacks? What are the serious drawbacks with traditional or conventional AC to DC converters? I have already discussed this with you in module 1, and for power electronics and electrical drives students with whom I am doing this power electronics simulation lab also, I am taking online classes. My dear students, we have simulated various types of single phase and three phase rectifiers and AC to DC phase controlled converters, and we have done FFT analysis of current drawn by converters under different loading conditions, and you have seen that the current drawn by these conventional or traditional AC to DC converters from the source, that is the AC current, is injected with the harmonics. It is distorted current, and this distorted current results in distortion in the voltage at the point of common coupling. And you have also seen through the simulations that these converters draw large reactive powers, especially at large delay angle or large firing angle values, right? To revise what we have already done through simulations, or just to brush up your memory, let me draw the circuit diagram of a single phase bridge rectifier, diode bridge rectifier, like this. And this single phase bridge rectifier is driving a purely resistive load, for example. Say purely resistive load. With this, there should be no power quality problem, because with purely resistive load, current drawn from source is purely sinusoidal, no problem, and no reactive power is drawn from the source. But as soon as you connect a filter capacitor across the load, this filter capacitor makes the source current, that is this IS, AC current or source current drawn by the rectifier from the source, it makes this current highly distorted. So you have seen through the simulations also in one of the simulation classes, this is the type of current which this type of rectifier is drawing from the source. If this is source voltage, the current drawn is like this, highly distorted current. This is the source current. It draws one current pulse in the positive half cycle. I mean, this rectifier draws one current pulse in the positive half cycle. Similarly, one current cycle in the negative half cycle. And if you remember, power electronics and electric drivers students, we have done the FFT analysis of this using Power GUI block, which is available in MATLAB Simulink software. And while doing the FFT analysis of this type of current, let me remind you that the harmonic level or distortion level in the current, in this type of current drawn by the converter from the source, which is also called total harmonic distortion. Do you remember? We have found the total harmonic distortion of this type of current. It was nearly 100%. That means current is highly distorted. Okay. Similarly, it depends upon the nature of load. I mean, if your load is like this, it is not resistive, it is highly inductive load, RL load, sufficiently inductive load, RL, with no filter capacitor. Then what type of current your rectifier will draw from the source? If you remember, let me remind you, we have done the simulation, and through the simulation also I have shown you that this is the type of current, that this is source voltage, of course, and this is the type of current which this rectifier draws from the source for this type of load. Again, you can see source current is not sinusoidal, it is non-sinusoidal. It is highly distorted. It is rectangular in nature or square wave. Okay, and if you remember through FFT analysis, we have found the THD, total harmonic distortion of this type of current. Let me remind you, let me refresh your memories. It was nearly 48%. 48% is again a very high value. That means this current is highly distorted. Okay, and through the FFT analysis, you have found, when you have drawn the harmonic spectrum of the current, this is the harmonic order, and this is harmonic current as a function of, or as a ratio between harmonic current to fundamental component of source current. This is harmonic component of source current divided by fundamental component of source current. If you remember, harmonic component of source current is harmonic order times the fundamental component of source current. So therefore, rather it is IS1 by H. It is fundamental RMS value of fundamental component of source current divided by H. Okay, so therefore, what is ISH by IS1? It is 1 by H, where H is the order of harmonics. For example, if harmonic is of order 1, which means fundamental component will have 100% amplitude. This is 100% in terms of percentage. It's fundamental component. Then the current drawn will have third harmonic component. This is third harmonic component, and it's ISH by IS1, which is equal to 1 by H. It will be equal to 1 by 3. Its amplitude is 1 by 3 of that of fundamental. Similarly, fifth harmonic component of current will have an amplitude of 1 by 5. Seventh harmonic component of current will have an amplitude of 1 by 7. Ninth harmonic component of current will have an amplitude of 1 by 9. 11th harmonic component of current, similarly with amplitude 1 by 11. 13th harmonic component of current has an amplitude of 1 by 13, and so on. This is the harmonic spectrum of current drawn by this type of rectifier for this type of load from the source. This is called harmonic spectrum. Fundamental component of current, IS1, is delivered to the load, and that represents the active power demand of the load. And these are all harmonic components: third harmonic component, fifth harmonic component, 7th, 9th, 11th, 13th, and so on, the higher order harmonic component. So that means whether your load is purely resistive with filter capacitor or RL type load, for this type of rectifier, the current drawn from source is highly distorted. And as per IEEE standard, there is one IEEE standard 1992, the harmonic distortion in the current, total harmonic distortion in the source current, should be less than or equal to 5%. If the current drawn by the rectifier or AC to DC converter from source has a THD of greater than 5%, that is not acceptable. So as per this standard, the source current or the AC current drawn by the converter from the source should have a THD of less than or equal to 5%. But you have seen that for this type of load, the THD is nearly 48%, and for purely resistive load with filter capacitor, the THD is nearly 100%. And for other type of loads, if this would have been a phase controlled converter, then and at large delay angles, large firing angles, THD would have been high, because as the delay angle increases, THD of the current increases. Current becomes more and more distorted. Okay. So therefore, this is one of the serious drawbacks of traditional AC to DC converters, whether they are rectifiers or phase controlled converters. That is, they inject high level of harmonics into the AC current. और ये AC current basically कहाँ से आती है? ये grid से आती है, distribution system से आती है. And when this distorted current flows through the feeder impedance, it causes distorted voltage drops across the feeder impedance. As a result of that, अगर ये आपका point of common coupling है, where other loads are also connected, ये समझ लीजिए point of common coupling जहाँ पे बाकी loads भी connected है. I will show here other loads. I will write here other loads. The voltage available here, the source voltage may be sinusoidal, but since this current is distorted, it causes voltage drop through the impedance of this. I can show it like this. This is source voltage, which is the grid voltage, which is purely sinusoidal. This is the grid feeder impedance, ZS. And when this source current, a highly distorted source current is flowing, it is drawn by the converter, AC to DC converter. It causes distorted voltage drops through harmonic voltage drops through this feeder impedance. As a result of which, अगर इस point of common coupling पे, this is the point of common coupling, इस पे बाकी loads भी connected है, बाकी consumers के, other loads. Those loads will receive distorted voltage. So distorted current causes distortions in the voltage at the point of common coupling, and as a result of which the other loads get distorted voltage and they also suffer because of non-sinusoidal voltage. Other problem with these traditional AC to DC converters, especially at large delay angles, is that they draw large reactive power. Okay, they draw because the fundamental component of current will lag behind the source voltage by large phase angle. और जितना delay angle, firing angle आप बढ़ाओगे, उतना phi भी बढ़ेगा, और जितना phi power factor angle बढ़ेगा, उतना power factor कम हो जाएगा. So because you remember the input power factor on the AC side of this converter is given by this formula, IS1 by IS into cos phi 1, where phi 1 is the phase angle between fundamental component of source current and the source voltage. Okay, so and for full converter, phase controlled converter, it is IS1 by IS cos alpha, because phi 1 is equal to alpha. So therefore, at large delay angles, large alpha, phi 1 also increases and cos alpha decreases, और आपका power factor poorer and poorer हो जाता है. Your power factor, input power factor becomes poor because of two factors, because of distortion in the currents, distortion factor, and because of large delay angle. और delay angle अगर large हुआ, cos phi कम हो जाएगा और input power factor कम हो जाएगा. And what does low input power factor mean? That means your rectifier or converter is drawing more and more reactive power from the source. Therefore, आपके source को, and since this type of converter along with this type of load, it draws distorted current from the source. Therefore, how does the source sees this converter along with this load? इसको कैसा लगता है? इसको ये non-linear load लगता है. If you put all this, आपके source को ये, this is your source. आपके source को ये load, converter, AC to DC converter based load, ये इसको non-linear load लगेगा. It will see it as a non-linear load, because although your source voltage is sinusoidal, but the current drawn is not sinusoidal, that is distorted, highly distorted. So therefore, there is a non-linear relationship between source voltage and source current. So therefore, this source sees your phase controlled converter or rectifier based load as non-linear load. And non-linear loads are known as drawing distorted currents, and hence distorting the voltages at the point of common coupling. And what are the practical examples of these nonlinear loads? Start from your homes, your inverter air conditioning system, your induction cooking system, your LED lighting system, television power supply, set-top box power supply, computer power supply, that's switch mode power supply, laptop power supply, UPS, home UPS or inverter जो हम घरों में use करते हैं. They are all the examples of these nonlinear loads, because all those loads, they use front end AC to DC converters, and these traditional AC to DC converters draw distorted currents from the source, and therefore the source sees your load as a nonlinear load. This is the main problem. So the serious drawbacks with traditional AC to DC converters and rectifiers is that they draw distorted currents, they act as nonlinear loads, and hence they result in distortion in the voltage at the point of common coupling, and hence they affect the operation of other devices, voltage sensitive devices also. And second problem is that they draw large reactive power from the source, especially at large delay or firing angles. So to overcome these problems, what is the solution to these problems? How can you solve these problems? You can solve these problems if you connect filters at the input side. And in fact, many years back, many decades back, of course, the researchers tried to improve the power quality of these traditional AC to DC converters by using passive filtering technique. They used passive filtering technique. In passive filtering technique, they used filters. For example, you can use filters like this, LC filters like this. This is one variety of LC filter. इसको आप line filter भी कहते हैं. This is your line passive filter, which is basically LC filter. Now, since for example, if this is a single phase AC to DC converter, it draws third harmonic, very strong third harmonic component. Apart from fundamental component, which is the actual useful component, it draws harmonic components, of which third harmonic is very strong. Fifth harmonic is also very strong. 7th, 9th, 11th, 13th, 15th, 17th, and other higher order harmonics. You cannot use a single passive filter for filtering all these harmonics. For suppressing each harmonic, you have to use single tuned filters. Just few classes back, one or two classes before, I have discussed with you passive filtering technique. In passive filtering technique, we use many single tuned filters, many single tuned, जिनको band pass filter भी कहते हैं, passive filters, single tuned passive filters. For example, you have to tune, you can use an LC filter, which is tuned to third harmonic only. What does it mean? It is tuned to third harmonic. It will provide very low impedance path to this third harmonic. It will trap it, it will arrest it. That means जो आपका load, non-linear load, third harmonic component source से draw कर रहा था, वो आप filter supply करेगा. So therefore आपकी source current free हो जाएगी of third harmonic. Similarly, if you want to eliminate fifth harmonic component of source current, you need another LC filter which is tuned to fifth harmonic. So another single tuned filter. Similarly, for suppressing or eliminating 7th harmonic, 9th, 11th, and 13th, you need 4 more single tuned filters. So how many single tuned filters you need? 1, 2, 3, 4, 5, 6. And these single tuned filters are very large in size. Why? Because what is your fundamental frequency, F1? That is 50 Hertz. If fundamental frequency is 50 Hertz, what will be the frequency of third harmonic component? Its frequency is 3 times fundamental frequency. That is 3 into 50, that means 150 Hertz. और जब 150 Hertz पे आप LC filter design करोगे, 150 Hertz is a small frequency. The size of filter will be very large. Similarly, what will be the frequency of fifth harmonic component? Frequency of fifth harmonic component will be 5 times fundamental, that is 250 Hertz, which is again not a high frequency, तो उसका size भी बड़ा हो जाएगा. Of course, the size of the single tuned filter, which is tuned to fifth harmonic component, will be smaller than that of, but it will be still higher. Similarly, the size of 7th harmonic tuned single tuned filter will be smaller than these two filters, but it will be still higher. The size of these single tuned filters sizes will be very large. और उसके बाद जो higher order harmonics आपके 15th, 17th, 19th, 21st, 23rd, so on, उनके लिए आप एक सिंगल हाई पास फिल्टर डिजाइन करोगे जिसका साइज छोटा होगा क्योंकि इनकी हार्मोनिक फ्रीक्वेंसी हाई है. And when you design filter at high frequency, the size decreases. The size of magnetics of the filter, magnetics means L and C, will be smaller and smaller if you design them at higher frequency. तो इनके लिए when you are designing a single high pass filter उसका size कम होगा. But what about the size of these single tune filters? They are at low harmonic frequencies. Their size will be very large. That will make the size of these passive filters, so many filters, very large. A whole assembly will become bulky and costly. And therefore, your source current may after that become something like this. It may not become purely sinusoidal. It may still have some level of distortion. It cannot make this source current purely sinusoidal. But you can say, okay, this source current may have reached some acceptable level. But at what cost? At the cost of large size of filters, which will make the whole assembly of your converter along with so many filters, the whole assembly will become very bulky, very costly, very heavy. Okay, so therefore passive filtering is not a better solution. Another solution is active power filtering. Active power filtering, and we have discussed in last few lectures about active power filters. One of the best active power filter which will address this current harmonic distortion is shunt active power filter. तो shunt active power filter में आप क्या करेंगे? If this is your phase controlled converter, you will have a shunt active power filter like this. यह आपका shunt active power filter है. This is its DC और ये इसका AC side. It will inject a filter current IF, for example, and this filter current will contain all the harmonics which are required by the load. So filter current will flow in this direction so that your source current is free of harmonics. So therefore harmonic compensation or harmonic elimination can be very effectively done by this single active power filter. And this active power, shunt active power filter will not have resonance problem, and it is adaptable to if your load parameters or source impedance changes, it automatically adjusts its filtering characteristics, unlike passive filters where your passive filter can detune if system parameters change, so if system conditions change, but it will not detune, it will effectively work. But the problem with this shunt active power filter is that its rating may be in some cases about 80% of the rating of the load. For example, if your load is 100 kilowatt, this rating of this may be around 70 to 80 kilowatt. So since its rating is very high, its cost also will be very high, and it is very complex to control it. Anyway, complexity in the control is not the problem, but problem is large rating and large high cost of this shunt active power filter. So then what is the solution? This was one of the greatest challenges faced by researchers, both power electronics engineers as well as power system engineers. Because as power electronics engineers or power systems engineers, they face this problem of harmonic distortion caused by these nonlinear loads, phase controlled AC to DC converters and rectifiers. And to solve these problems, first they came up with the solution of passive filters. But passive filters, they found that so many single tuned filters are required, which will make the system bulky, heavy, costly. And then passive filters have other drawbacks, which we have discussed in one of the previous classes, like fixed compensation. They may detune if the system conditions change. They have the problem of parallel resonance and so on. Then passive filtering was replaced by active power filtering. Active power filtering does not have those problems of passive power filters. They very effectively do the harmonic compensation, but the rating and cost of active power filter also was found to be very high. Then there was a group of researchers who said that why not to design an AC to DC converter which does not act as a nonlinear load, but which acts as a linear load. In other words, which does not have these harmonic and reactive power problems, which draws purely sinusoidal currents under all conditions from the source, and which draws the source current which is in phase with the voltage, giving unity power factor operation. This was a group of researchers who worked towards this. Thanks to power's advancement and development in power semiconductor technology and development in sensor technology and development in digital signal processors and microprocessors, this dream could be fulfilled. This dream, which was dreamt by some researchers, some engineers, that instead of having traditional AC to DC converters, why not have a modern AC to DC converter which will not have these problems, which will not distort the source current, line current, which will keep them sinusoidal and keep them in phase with their respective phase voltages, giving unity power factor operation. For that, it was necessary that these thyristors were replaced by modern power semiconducting devices like power transistors, that is power bipolar junction transistors, BJTs, power MOSFETs, GTOs, IGBTs और IGCTs, या आजकल और भी नए devices आ रहे हैं, IGCTs, etc. The rapid development which has taken place in power semiconductor technology along with computer technology has made it possible to replace these thyristors, SCRs, by any of these self-commutated power semiconducting devices like IGBTs or GTOs or power MOSFETs, and switch them at a very high switching frequency in such a way that they draw purely sinusoidal currents from the source. And they act as linear loops. And that new breed of power converters, so this gave rise to new breed or new generation of AC to DC power converters. And this new breed of AC to DC power converters was called improved power quality converters, IPQCs, or high power factor converters, or power factor correction converters, or switched mode rectifiers, or PWM rectifiers. All these converters, they do not use SCRs largely. They use modern self-commutated power semiconducting devices like power transistors for very low power range, or power MOSFETs for high switching frequency and low power range, or IGBT for medium power range, or GTOs for high power range. Okay. So, therefore, the realization of improved power quality converters was possible because of availability of these self-commutated modern power semiconducting devices like IGBTs, power MOSFETs, etc. And because of availability of highly precise voltage and current sensors, and because of the availability of high-speed digital signal processors where you could implement your control algorithm very fast. Okay. Now, what are the types of improved power quality converters? If you take IPQCs, they are of two types. They are unidirectional improved power quality converters, and they are bidirectional improved power quality converters. And whether they are unidirectional or bidirectional improved power quality converters, I mean, if you take, for example, unidirectional improved power quality converters, there again, they may be operating in discontinuous conduction mode or continuous conduction mode of operation. Similarly, bidirectional improved power quality converters, they mainly operate in continuous conduction mode of operation. Now, in applied power electronics, I am talking to, I'm addressing power electronics and electrical drives students of this course who are doing this course. And for electrical power and energy systems EPS students, those of you who have done a course at BTech on advanced power electronics or even basic power electronics, you must have studied various types of DC to DC converters, like DC to DC buck converter, जिसको step down chopper भी कहते हैं. Similarly, DC to DC boost converter, which is also called step-up chopper. Similarly, DC to DC buck boost converter, which is also called step-down and step-up chopper. Then choke converter, then flyback, DC to DC flyback converter, DC to DC forward converter, and so on. And I know Dr. Tabish Nazir is already teaching PEED students in applied power electronics. She has already taught you various types of DC to DC converters in this semester, in this session itself. DC to DC buck converter, boost converter, buck boost converter, choke converter, flyback converter, forward converter, push-pull converter, half bridge converter, full bridge converter. And it has been found that these DC to DC converters, when they are operating in discontinuous conduction mode of operation and when they are connected to a rectified AC line, they give self-power factor correction. They have self-power factor correction property. So I will write here DC to DC converters operating in discontinuous conduction mode of operation, DCM, when connected to rectified AC line. I'll come to this, I'll explain it. When connected to a rectified AC line, give self power factor correction, which is also called self PFC property. That means you already know your DC to DC buck converter, for example, looks like this. You already done it in your course, maybe in BTech course, and now in advanced or applied power electronics course also you are doing this. It looks like this. Your DC to DC buck converter looks like this. For example, there is output filter also, and this is your load. Load voltage is V0 and load current is I0. This is output filter. Output filter for filtration of load voltage, making it ripple free, and load current also. This is buck converter. This is basically DC to DC buck converter. Input is DC, output is controlled DC. Why is it called buck converter? Because output voltage is always less than input voltage. At the most, that will be equal to input voltage when duty ratio is 1. Otherwise, output voltage is always less than input voltage. That's why it's called buck converter. Now, when this DC to DC buck converter is connected to rectified AC line, rectified AC line means this. You have a single phase bridge rectifier which is connected to AC source Vs, and you may have some filter also here, line filter. I will write here line passive filter, LC filter hoga, line passive filter. And you know, when this DC to DC converter, ये DC to DC buck converter, जब आप rectified DC line के साथ, rectified AC line के साथ connect करेगी, ये आपकी rectified AC line है. See, this is DC here, of course. ये आपका DC यहाँ पे आ रहा है, VDC. लेकिन ये बैटरी से नहीं आ रहा है, ये DC सोर्स से नहीं है. कहाँ से आ रहा है? ये rectified AC line से आ रहा है. ये आपकी AC है, and this bridge rectifier converts this AC into DC. So this is called rectified AC line. So when you are feeding your load through a DC to DC converter which is connected to a rectified AC line, then this becomes your AC to DC buck converter. अगर आप बैटरी से इसको सप्लाई कर रहे हैं तब ये DC to DC buck converter है. Then this is DC to DC buck converter. इसमें AC है ही नहीं कहीं. लेकिन but if you are not supplying it from DC source, but you are supplying it from AC source but through a rectifier. That means when you are connecting your DC to DC buck converter to a rectified AC line, then it becomes AC to DC buck converter. Because your input is not now DC, your input is AC, and output is controlled DC. And in this case, output voltage is always less than peak input voltage. So that in that case, it becomes AC to DC buck converter. And it has been found by researchers then when these DC to DC converters, for example, इस केस में मैंने DC to DC buck converter लिया, when it is connected to rectified AC line, it automatically gives self-PFC property, self power factor correction property. That means it draws the source current from the source AC current. Of course, in presence of a small filter, which is sinusoidal in nature and which is in phase with the voltage, giving nearly unity power factor, जिसको सेल्फ पावर फैक्टर करेक्शन प्रॉपर्टी देते हैं. अगर आप इस लोड को रेक्टिफायर से डायरेक्टली सप्लाई करते थे, डीसी टू डीसी कन्वर्टर बीच में नहीं होता, या फेज कंट्रोल कन्वर्टर से कनेक्ट ये सप्लाई देते लोड वोल्टेज को विद firing angle control, then your source current would have been highly distorted and you would never get power factor correction. But if your load is supplied by DC to DC converter, not AC to DC converter, but this DC to DC converter is connected to rectified AC line, then the source current drawn from the source by this AC to DC buck converter, or it may be later on AC to DC boost converter, etc., this current becomes very nearly sinusoidal and it has self power factor correction property. That means the input power factor becomes nearly unity. This has been found one of the properties of DC to DC converters. Then when DC to DC converters but operating in DCM, but the condition kya hai yahan? These DC to DC converters should operate in discontinuous conduction mode. When any type of DC to DC converter operating in DCM is connected to rectified AC line, it has self power factor correction property and it automatically becomes improved power quality converter. Let us take them one by one. Now we have various types of DC to DC converters. पहला हमारा है DC to DC buck converter. तो जब उसको मैं rectified AC line के साथ connect करूँगा, वो that will become AC to DC buck converter. So the first topology that I am going to discuss with you is AC to DC buck converter. AC to DC buck converter basically comprises of a DC to DC buck converter which is connected to rectified AC line. So it looks like this. Let me draw the power circuit diagram first. This is source voltage and here आपकी source current IS है and you have a small LC filter here. इसको हम line filter कहते हैं. You have a line filter which is of course a passive filter, passive LC filter. But unlike those single tuned filters, ये एक ही filter होगा और इसका size बहुत छोटा होगा. इसका size छोटा क्यों होगा? I will come to that later on. Okay, now this rectified output यहाँ आपका है VDC या VL है, इसे कहेंगे. Output voltage is VL. And उसके बाद this rectifier is followed by DC to DC buck converter. This is self-commutated switch. It may be a power transistor or a power MOSFET or IGBT or GTO. ठीक है? So then you know buck converter has a freewheeling diode like this. Then it has an output filter like this. This is output filter and you have a load. Load resistance R है. Load के across voltage है variable voltage V0. It's a variable voltage and load current है I0. So this is your AC to DC buck converter. अब इस AC to DC buck converter में अगर आप source voltage waveform देखेंगे, this is source voltage waveform 0, pi, 2 pi and so on. This is source voltage waveform. What type of let us suppose filter नहीं है वहाँ. In absence of filter, यहाँ मैं लिखूँगा without line filter. Suppose line filter connected नहीं है. This passive LC filter connected नहीं है. Without line filter, when the switch is closed by the control algorithm, when, for example, this switch may be an IGBT like this, with 3 terminals, collector, emitter and gate. When control pulse is high at the gate terminal, so the switch will go into conduction, current will flow from collector to emitter, it will act as a closed switch. और जब ये क्लोज हो जाएगा तो यहाँ पे लाइन करंट IL फ्लो होगी जो लोड की तरफ जाएगी. And basically this line current basically comes from source. ओके अगर सोर्स का पॉजिटिव हाफ साइकिल है, सो दिस एंड दिस पेयर ऑफ डायोड्स विल बी कंडक्टिंग और करंट इस तरफ फ्लो होगी। और जब ये स्विच ऑफ हो जाएगा, आई मीन व्हेन द पल्स इज लो, स्विच ऑटोमेटिकली ऑफ हो जाएगा, टू एक्ट एज एन ओपन स्विच, ये करंट खत्म हो जाएगी। लोड में तो करंट फ्लो होगी बिकॉज ये दिस कैपेसिटर इज ऑलरेडी देयर, कैपेसिटर विल सप्लाई पावर टू द लोड एट दैट टाइम, बट सोर्स से कोई भी करंट नहीं आएगी। So that means as long as the switch is closed, control pulse is high here at the gate terminal of IGBT. Switch is closed, so current is drawn from the source. And when control pulse at the gate terminal of IGBT is low, ये switch off हो जाता है, no current comes from source. So therefore आपकी source current इस तरह आएगी. It will be in the form of a pulse. यहाँ तक स्विच ऑन है, सो करंट सोर्स से आ रही है, और जब स्विच ऑफ हो गया, सोर्स से करंट जीरो हो गई। उसके बाद नेक्स्ट कंट्रोल पल्स आती है आफ्टर सम टाइम से, उसके बाद नेक्स्ट कंट्रोल पल्स आती है। जब नेक्स्ट कंट्रोल पल्स आती है, स्विच फिर से ऑन हो जाता है और फिर ऑफ हो जाता है। ऑन और ऑफ के दौरान ये करंट ड्रॉ करेगा फिर से, बट द एम्पलीट्यूड ऑफ दिस करंट इज हायर देन द फर्स्ट करंट। दूसरी करंट पल्स का एम्पलीट्यूड पहली करंट पल्स से ज्यादा होगा, बिकॉज दूसरी करंट पल्स हायर वोल्टेज पे आती है। पहली करंट पल्स के टाइम सोर्स वोल्टेज लो थी, सो लो ड्रॉज स्मॉल करंट। दूसरी करंट पल्स जब आती है, उस वक्त सोर्स वोल्टेज यहां तक हो जाती है, इट इज हायर। एट हायर सोर्स वोल्टेज द करंट ड्रॉन इज हायर। तीसरी करंट पल्स लेट अस से पीक वैल्यू ऑफ सोर्स वोल्टेज पे आती है, तो इसका एम्पलीट्यूड सबसे हाई होगा। द नेक्स्ट करंट पल्स लो होगी और नेक्स्ट करंट पल्स फिर से लो होगी। सो दिस इज इन द पॉजिटिव हाफ साइकिल। आई हैव शोन 5 पल्सेस। कितनी पल्सेस होगी वो डिपेंड करता है आप पॉजिटिव हाफ साइकिल में कितनी बार ये स्विच ऑन और ऑफ करते हो। जनरली वी टर्न ऑन एंड ऑफ दिस स्विच थाउजेंड्स ऑफ टाइम्स। फॉर एग्जांपल अगर आपकी स्विचिंग फ्रीक्वेंसी स्विच की 5 किलोहर्ट्ज है, सो 5000 टाइम्स इट विल बी ऑन एंड ऑफ इन वन साइकिल। दैट मीन्स आधे साइकिल में 2500 टाइम 2500 times on or off होगा। So how many current pulses you will get in positive half cycle? 2500 times, 2500 current pulses, small current pulses। मैं तो यहाँ 5 ही दिखाता हूँ क्योंकि I cannot show thousands of pulses here, it's not possible। But it depends upon आपने switching frequency कितनी choose की है। For example, if I have chosen a switching frequency of the switch of 1 kilohertz, 1 kilohertz means 1000 hertz। That means ये switch 1000 times on or off होगा पॉजिटिव और नेगेटिव हाफ साइकिल में, मतलब एक साइकिल में। दैट मीन्स 500 cycles, 500 current pulses will be there in positive half cycle and 500 current pulses will be there in negative half cycle. But here I am showing only 5 pulses in positive half cycle and similarly 5 pulses in negative half cycle. So this is the nature of source current, IS. अब आपकी सोर्स करंट फिल्टर के बगैर ऐसी है। नाउ यू मे आस्क अ क्वेश्चन, सर व्हाट इज द एडवांटेज ऑफ दिस? विदाउट दिस डीसी टू डीसी बक कन्वर्टर इट वुड हैव बीन नॉन साइनसॉइडल लाइक दिस, इट वुड हैव बीन समथिंग लाइक दिस व्हिच इज वेरी रिच इन हार्मोनिक्स। अभी भी तो ये साइनसॉइडल नहीं है, इट्स वेरी रिच इन हार्मोनिक्स। या ऑफ कोर्स आई एग्री विद यू, अगर आप इसका एफएफटी एनालिसिस करेंगे वहाँ मैटलैब सॉफ्टवेयर से, इसका टीएचडी भी बहुत आएगा, मे बी 40-50% इसका टीएचडी आएगा या उससे भी ज़्यादा। दैट मीन्स दिस करंट स्टिल हैज़ वेरी हाई लेवल ऑफ डिस्टॉर्शन। लेकिन आपको मैडम ने पल्स विड्थ मॉड्यूलेशन में पढ़ाया होगा कि पल्स विड्थ मॉड्यूलेशन का एडवांटेज है दैट द फ्रीक्वेंसी ऑफ हार्मोनिक्स इट इंक्रीजेस, इट शिफ्ट्स ऑल द हार्मोनिक्स टू हाई फ्रीक्वेंसी साइड। अभी थोड़ी देर पहले मैंने आपको हार्मोनिक स्पेक्ट्रम सोर्स करंट का दिखाया था। फंडामेंटल इज 100%, थर्ड हार्मोनिक हैज an amplitude of 1/3, fifth harmonic has an amplitude of 1/5, seventh harmonic has an amplitude of 1/7, ninth harmonic has an amplitude of 1/9 and so on। अब मैं क्या कर रहा हूं, I am instead of having only one current pulse in one half cycle या एक square wave positive half cycle में और एक square wave negative half cycle में, I have thousands of current pulses in positive half cycle and thousands in negative half cycle। उसको पल्स विड्थ मॉड्यूलेशन कहते हैं। उसका एडवांटेज ये है कि आपकी करंट की हार्मोनिक डिस्टॉर्शन अभी भी बहुत हाई है, इट मे बी 50% और मोर देन 50%, बट देयर विल बी नो लोअर ऑर्डर हार्मोनिक्स। द मोस्ट प्रिडोमिनेंट हार्मोनिक इस केस में, अगर आपकी करंट इस टाइप की है या इस टाइप की है जो आपका कन्वेंशनल एसी टू डीसी कन्वर्टर ड्रॉ करता है, द मोस्ट प्रिडोमिनेंट हार्मोनिक इज थर्ड, followed by fifth, followed by seventh, and so on. If you are using this AC to DC buck converter or operating your buck converter at a very high switching frequency, you get hundreds or thousands of current pulses in each half cycle. उससे advantage ये होगा that the most predominant harmonic will be around the switching frequency. For example, अगर आपकी switching frequency 5 kHz है, तो आपका पहला हार्मोनिक थर्ड हार्मोनिक नहीं आएगा, वो 5 kHz के आसपास आएगा। नेक्स्ट हार्मोनिक इसके डबल स्विचिंग फ्रीक्वेंसी पे आएगा, 2 5 10 किलोहर्ट्ज के आसपास आएगा। नेक्स्ट आएगा 3 5 और 15 किलोहर्ट्ज के आसपास। यानी अगर आप इस करंट का हार्मोनिक स्पेक्ट्रम ड्रॉ करोगे, लेट मी शो यू हार्मोनिक स्पेक्ट्रम ऑफ दिस टाइप ऑफ करंट। दिस इज H, दिस इज ISH by IS1 which is equal to 1 by H। फंडामेंटल कंपोनेंट ऑफ करंट तो है ही 100%, इट्स ऑलरेडी देयर। There will be no third harmonic component. There will be no fifth harmonic, no seventh, no 11th, no 13th, no 15th, no 17th. Lower order harmonic सारे खत्म हो जाएंगे। तो आपका पहला हार्मोनिक स्विचिंग फ्रीक्वेंसी के आसपास आएगा। स्विचिंग फ्रीक्वेंसी आपकी है FH। अब ये डिपेंड करता है आपने स्विचिंग फ्रीक्वेंसी कितनी यूज किया। आपने अगर आपने स्विचिंग फ्रीक्वेंसी इस स्विच की 1 किलोहर्ट्ज यूज की है, तो आपका पहला हार्मोनिक 1000 हर्ट्ज के आसपास आ जाएगा। एंड इफ यू आर स्विचिंग इट एट 5 किलोहर्ट्ज, तो आपका पहला हार्मोनिक 5 किलोहर्ट्ज के आसपास आएगा और उसका एम्पलीट्यूड नेग्लिजिबली स्मॉल होगा, बिकॉज एज यू गो टुवर्ड्स हायर ऑर्डर हार्मोनिक्स, हाई फ्रीक्वेंसी, एम्पलीट्यूड कम होता है। अभी भी थोड़ी देर पहले आपने देखा था थर्ड हार्मोनिक का हायर एम्पलीट्यूड है, फिफ्थ का कम है, सेवेंथ का और कम, नाइन्थ का और कम। 5000 हर्ट्ज के हार्मोनिक का एम्पलीट्यूड कितना होगा? ये बहुत कम होगा। नेक्स्ट हार्मोनिक आपका आएगा फिर 2 टाइम्स स्विचिंग फ्रीक्वेंसी पे। ये अगर FH है, ये 2FH है, 2 टाइम्स स्विचिंग, उसका हार्मोनिक कंटेंट इतना कम होगा कि आपको स्कोप, ऑसिलोस्कोप पे वो दिखेगा भी नहीं। सिमिलरली नेक्स्ट विल बी एट 3FH, नेक्स्ट विल बी 4FH एंड सो ऑन। सो आपके ये करने से क्या हुआ? आपके ये करने से ये हुआ, हाई स्विचिंग फ्रीक्वेंसी पे DC टू DC कन्वर्टर को ऑपरेट करने से ये हुआ कि आपकी सोर्स करंट में अगर आप THD निकालेंगे, THD कम नहीं होता, इट इज स्टिल डिस्टॉर्टेड, बट ऑल हार्मोनिक्स आर शिफ्टेड टू हाई फ्रीक्वेंसी साइड। नाउ यू मे अगेन आस्क अ क्वेश्चन, व्हाट इज द फन ऑफ शिफ्टिंग ऑल harmonics to high frequency side? I told you earlier that when you design a filter, the size of filter becomes extremely small if you design the filter at high frequency. अगर आप इससे पहले थर्ड हार्मोनिक, आपकी फ्रीक्वेंसी थर्ड हार्मोनिक आ रहा था, थर्ड हार्मोनिक से दिस वाज योर थर्ड हार्मोनिक, और थर्ड हार्मोनिक पे व्हाट वाज द साइज ऑफ फिल्टर? वेरी लार्ज, बिकॉज थर्ड हार्मोनिक फ्रीक्वेंसी मींस 3 into 50 150 हर्ट्ज। फिफ्थ हार्मोनिक पे नेक्स्ट सिंगल टून फिल्टर आप डिजाइन करते थे, और वो किस फ्रीक्वेंसी पे करते थे? 5 into 50, दैट्स 250 हर्ट्ज। उसका साइज भी हाई आता। यहाँ किस हार्मोनिक फ्रीक्वेंसी पे, किस फ्रीक्वेंसी पे आपको फिल्टर डिजाइन करना है? FH, switching frequency, which is 5 kilohertz, then 10 kilohertz, then 15 kilohertz, and designing the filter at such a high frequency, the size of filter will be extremely small. ये इतना छोटा होगा कि आप प्रिंटेड सर्किट बोर्ड पे इसको, आपका इंडक्टर इतना छोटा दिखेगा, कैपेसिटर इतना छोटा दिखेगा, और आप इसको प्रिंटेड सर्किट बोर्ड पे आराम से सोल्डर कर सकते हो। इट विल नॉट बी अ वेरी लार्ज फिल्टर, it will not be of the size of this board, it will be a small filter. So therefore now the size of this line filter, जो line filter आप यहाँ रखेंगे, ये high pass filter होगा और ये एक ही filter होगा, उसको आप high switching frequency पे डिजाइन करेंगे, and at high switching frequency the size of magnetics, that the size of inductor and capacitor is extremely small. ये इतना छोटा होगा कि ये आपको दिखेगा भी नहीं, it will be such a small filter, और ये एलिगेंटली सारे हाई फ्रीक्वेंसी हार्मोनिक्स को एलिमिनेट करेगा। और देयरफॉर फिल्टर की प्रेजेंस में आपकी करंट इस तरह आएगी। दैट मींस इफ दिस इज योर सोर्स वोल्टेज, दैट इज सपोज आइडियली आपकी सोर्स करंट प्योरली साइनसोइडल आएगी, because it will remove all high frequency harmonics. This is the advantage of operating a buck converter at high switching frequency and connecting it to rectified AC line. जब आप इसको rectified AC line के साथ कनेक्ट करते हैं, ये आपका AC to DC buck converter आ जाता है, बन जाता है, और विदाउट फिल्टर इसकी सोर्स करंट ऐसी दिखती है, जिसका एडवांटेज है कि all harmonics, there are no lower order harmonics, all harmonics are shifted to very high frequency, around switching frequency, and it is very easy to filter those harmonics at a very high frequency by a small line filter. And when you are connecting a small passive LC filter, line filter, you get almost nearly sinusoidal current. Source current becomes nearly sinusoidal and in phase with the voltage. So therefore this buck converter gets self-PFC property. Self-PFC property. And it automatically becomes improved power quality AC to DC converter, because what type of current it is drawing? Purely sinusoidal current, and in phase with the voltage. That means it is neither drawing harmonics nor is it drawing reactive power. So therefore आपका ये converter, AC to DC converter, source को कैसा दिखेगा? It will appear as a linear load. It will appear as a linear load. This is how you design an improved power quality converter. अच्छा, चलिए आगे चलते हैं. Let me now draw some waveforms. या आपकी switch की waveform है. ये S on है, और during this period आपका switch S off है, and then it is again on, S on, and so on. So therefore आपकी ये current है, ये rectifier के output पे जो current है IL, या आपकी source current IS, when the switch is closed, this current increases, and when switch is opened, it immediately becomes equal to 0. और दूसरी करंट आपकी यहाँ आएगी, इसका एम्पलीट्यूड पहले करंट पल्स से हाई आएगा, क्योंकि यहाँ सोर्स वोल्टेज का इंस्टेंटेनियस वैल्यू नेक्स्ट टाइम हायर होगा. सो दिस इज DTS, यहाँ से यहाँ तक DTS है, और ये टाइम पीरियड TS है. अगर इसमें आप ना, इफ यू अप्लाई मैथमेटिक्स, इसकी मैथमेटिकल एनालिसिस वगैरह करोगे, यहाँ जो ये लाइन करंट आपको यहाँ रेक्टिफायर के आउटपुट पे DC लाइन करंट निकलती है, एक साइकिल में, ये एक साइकिल में, एक टाइम पीरियड में इसका एवरेज वैल्यू अगर आप निकालोगे, IL एवरेज, that is given, that will be given by this equation, d square TS by 2L into VLT minus d square TS by 2L into V0. V0 आपकी आउटपुट वोल्टेज है. I'm not deriving it. For derivation, you can refer to the research paper जो मैं at the end of this lecture आपको दूंगा, जिस research paper से मैंने ये content लिया. It is not this, you will not get from any book. You will get it from one of the IEEE research papers, conference papers. IL average is given by this expression. अब अगर आप, now if you draw the characteristics like this, characteristics of the converter. This is, for example, source voltage VST, and this is source current IST. I want to see the relationship between source voltage and source current. This is 0. और नीचे आपकी for example source voltage है. ये waveform source voltage है. This is pi. This is 2 pi, and so on. This is source voltage. ये ओमेगा टी एक्सिस है, और इस ओमेगा टी एक्सिस पे मैं अब सोर्स करंट देखना चाहता हूँ, इसकी वेव फॉर्म देखना चाहता हूँ. द रिलेशनशिप बिटवीन सोर्स वोल्टेज एंड सोर्स करंट विल बी लाइक दिस. इट विल हैव लीनियर रिलेशनशिप, लेकिन ये यहाँ 0 से लीनियर रिलेशनशिप परफेक्ट होती है अगर ये ऐसे 0 ओरिजिन से स्टार्ट होती. लेकिन यहाँ से 0 से यहाँ तक देयर विल बी नो करंट. उसका रीज़न ये है कि आपका ये DC to DC बक कन्वर्टर ऐसे इट्स लाइक दिस. आई डोंट हैव मच स्पेस हियर, देयरफॉर मुझे वो डायग्राम रब करनी पड़ी. यह आपका AC to DC बक कन्वर्टर है। लोड के अक्रॉस वोल्टेज V0 है। फॉर एग्जांपल अगर ये आपकी, इफ दिस इज योर सोर्स वोल्टेज VS, load voltage is, let us say, V0. Why is it called buck converter? Because output voltage, DC output voltage, is always less than peak of AC input voltage. It's less than peak of AC input voltage. Because in input voltage AC है, उसका peak ले लीजिए, output voltage हमेशा AC input voltage के peak से कम होती है. That's why it's called AC to DC buck converter. This is your input voltage, which is AC. Output voltage is perfect DC. अब आप देख सकते हैं यहां से यहां तक, from this zero to this point, instantaneous value of source voltage is less than output voltage. And when this source voltage is less than output voltage, even if you are closing the switch, no current will be flowing from this side to this side. Reason? Because current cannot flow from low potential to high potential. So from this point to this point, source voltage is less than output voltage. So even if you are issuing control pulse to the IGBT close भी हो जाता है, but it will not draw any current from the source. Why? Because the instantaneous value of the source voltage is less than output voltage. So that is why यहाँ से यहाँ तक आप देख सकते हैं your converter does not draw any current from the source in positive half cycle as well as in the negative half cycle. That is why अगर आप इसकी current की wave form देखोगे, it should have been like this, but लेकिन ऐसी नहीं दिखेगी. करंट, सोर्स करंट कुछ ऐसी दिखेगी. यहां से यहां तक, which is this region, since instantaneous value of input voltage is less than DC output voltage, your converter will not draw, there is no current which will be drawn from the source. So therefore source current यहाँ से यहाँ तक zero है. उसके बाद source current sinusoidally vary होती है. Of course in presence of filter. Without filter वो ऐसे होगी, pulsed. But in presence of filter it will be like. Similarly negative half cycle में अगर ये pi है, pi से यहाँ तक no current will be drawn. So this is the nature of current drawn by your AC to DC buck converter. ये source voltage है और ये source current है. This is the relationship between source voltage and source current. I can sum up it here. If this is your source voltage, एक साइकिल में लेता हूं, आपकी source current ऐसे दिखेगी. No doubt it is sinusoidal, but it is still discontinuous. यहाँ से यहाँ तक, यहाँ से यहाँ तक, it is still discontinuous. It is because of this reason that although AC to DC buck converter gives sinusoidal current, it improves the input power factor, but because the current for some period here near zero crossings is discontinuous, so therefore this AC to DC buck converter is not a very good candidate for self PFC property. So I will write not a good candidate for self power factor correction, self PFC. It improves, no doubt, input power factor, and it improves the quality of current also, but still the quality of current is not what we desire. So therefore AC to DC buck converter is not a good candidate for self PFC. Let us quickly go to next category of AC to DC converter, that is AC to DC boost converter. First one was AC to DC buck converter. Now we will study AC to DC boost converter. Now you can see why it is called boost converter, because DC to DC boost converter in this case is connected to a rectified AC line. ये आपकी rectified AC line है. This is your source voltage. Source. This is your line filter. I will write here passive LC filter, or you can call it line filter. This is source current. और आगे आपका boost converter है. And if you remember, this boost converter ऐसे दिखता है. Your DC to DC boost converter looks like this. You have to please, when you watch this lecture and study these types of improved power quality AC to DC converters like AC to DC buck converter, boost converter, and others operating in discontinuous conduction mode of operation, you please first of all brush up, revise your DC to DC converters, DC to DC buck converter, boost converter, and other converter topologies. This is load voltage and this is load current. This is your rectifier output voltage VL and this is rectifier output current IL. Now this is your boost converter. A boost converter में when this switch is closed, current IL flows, it's drawn from the source से भी current आएगी. That means अगर ये source voltage है आपकी VS 0 by, मैं filter के बगैर दिखाऊंगा, when switch is closed, say at omega t equal to 0 itself, इसमें वो वाली problem नहीं है. When switch is closed, current flows like this and energy is stored in the inductor. वो current source से आएगी, ऐसे आएगी, rise होगी और फिर fall होगी. Fall कब होगी? When switches, because you are operating this switch at a very high switching frequency. आप immediately switch को off करते हो और आप जब switch को off करते हो ये current एकदम zero नहीं हो जाती है, ये current धीरे धीरे zero हो जाती है. धीरे धीरे क्यों? Because this current then energy, this inductor releases the energy and supplies energy to the output stage, and when it supplies energy to the output stage, current decreases. I will repeat, when the switch is closed, current through the inductor increases, and when switch is open, current through the inductor decreases slowly. Or since you have to operate this boost converter in discontinuous conduction mode, आपको wait करना है जब तक ये current zero नहीं हो जाती. अब देखिए current zero हो गई. As soon as it becomes zero, आप next switching कर लीजिए. Close the switch again, current will again rise, but amplitude of the second current pulse will be greater than first current pulse, because first current pulse के वक्त voltage near zero थी. Second current pulse के time instantaneous value of input voltage is higher, so it will it will inject more amplitude of current. It will increase, और जब switch open करेंगे आप, ये decrease धीरे धीरे हो जाएगी. Similarly, like this, like this, like this. This is positive half cycle. Similarly, negative half cycle में भी ऐसे ही होगा. So this is. So अगर मैं wave form में दिखाऊंगा यहाँ एक, this is switch on, switch off, and then again switch on and so on. This is source current IS. पहली बार जब switch on हुआ तो ये rise हो जाएगी और जब off हुआ तो fall हो जाएगी. जब दूसरी बार switching होगी, it will rise again and fall again. But amplitude of second current pulse is greater than first current pulse. ये आपका DTS है और ये total time period TS है. ये D1 है. What is D1? D1 is the inductor discharge time. During this period, current through the inductor increases, inductor charges. And during this period, the current through the inductor decreases, inductor discharges. And the period or ratio, time ratio during which the inductor discharges, that's called D1. That is D1. Okay. Now this, mathematically, this average DC output current, IL average, it is given by this equation now. 1 by Ts times 1 by 2 into D plus D1 into Ts into VLT by L into DTS. Okay. अब जब आप इसको प्लॉट करते हो, लेट मी शो यू दोज वेव फॉर्म्स जो इससे पहले मैंने आपको दिखाई थी. दिस इज VS IS, सोर्स वोल्टेज, सोर्स करंट, और ये आपकी सोर्स वोल्टेज है, वो ये है. दिस इज सोर्स वोल्टेज प्योरली साइनसॉइडल, और आपकी सोर्स करंट दिस ओमेगा टी, और आपकी सोर्स करंट आप यहां दिखा सकते हैं. दिस इज सोर्स करंट IS. द रिलेशनशिप बिटवीन VS एंड IS विल बी, नाउ इट विल स्टार्ट फ्रॉम जीरो इटसेल्फ. अनलाइक बक कन्वर्टर जहां पे यहां से यहां तक करंट नहीं होती थी, बट यहाँ बूस्ट कन्वर्टर में वो प्रॉब्लम नहीं है. ओके, इट विल राइज लाइक दिस उसके बाद ऐसे जाएगी, सिमिलरली नेगेटिव हाफ साइकिल में ऐसे, and your current source current will be like this. ये देखिए ना, इसमें वो प्रॉब्लम नहीं थी जैसे बक कन्वर्टर में थी, दैट नियर जीरो क्रॉसिंग इट वाज नॉट ड्राइंग एनी करंट because instantaneous value of input voltage was less than the DC output voltage. इसमें वो प्रॉब्लम नहीं है क्योंकि इसमें the source current is determined by inductor current. Even if your output voltage is higher than input voltage, when you are closing the switch, current has to flow through this path, not through the load. तो आपकी output voltage matter ही नहीं करेगी यार. That's why current starts rising right from zero crossing. So therefore अगर ये आपकी source voltage है, एक cycle में लेता हूँ 0 पाई 2 पाई सोर्स वोल्टेज, सोर्स करंट आपकी जीरो से ही स्टार्ट होगी और सोर्स करंट कुछ ऐसे होगी. जबकि बक कन्वर्टर में इफ दिस वाज सोर्स वोल्टेज, सोर्स करंट ऐसे थी, जीरो क्रॉसिंग के पास सोर्स करंट नहीं होती थी, लेकिन इसमें ऐसा नहीं है. So therefore your boost converter is a better converter. Now why is it called boost converter? Because output voltage is always greater than peak input voltage. Vs peak, peak input voltage से हमेशा ज़्यादा होगा. Why I am calling peak input voltage? Because your input voltage is AC. उसका peak value होता है √2 times RMS value. So it is greater than √2 times RMS value. Output voltage is always greater than peak input voltage. That's why it's called boost converter. Anyway, that we already know. So it's the waveform is better. But लेकिन इसमें आप देख सकते हैं थोड़ा नॉन लीनियर रिलेशनशिप है. I mean आपकी करंट लीनियरली, परफेक्टली लीनियर ऐसे होती, स्ट्रेट लाइन एग्जैक्टली. ये पहले स्ट्रेट है, उसके बाद थोड़ा डिविएट हो जाती है. इट इज बिकॉज ऑफ दिस इंडक्टर करंट की डिस्चार्ज है ना. अगर इंडक्टर करंट आपकी यहीं पे जीरो हो जाती, यहीं पे जीरो हो जाए, लेकिन ये पहले चार्ज होती है और फिर धीरे धीरे डिस्चार्ज होती है, चार्ज होती है धीरे धीरे डिस्चार्ज होती है. एंड बिकॉज ऑफ द प्रेजेंस ऑफ दिस D1 इज दिस पीरियड, there is some non-linearity in the current, so that your no doubt in source current is in phase with the voltage. It gives almost unity input power factor, but it is not perfectly sinusoidal. Sinusoidal है ये, लेकिन perfect sinusoid नहीं है, but it is still better than buck converter. So we can say it's a good candidate for self PFC, boost converter. Okay, let us quickly go to third type of improved power quality converter, that's called AC to DC buck boost converter. Buck boost converter. Now the name itself suggests that it comprises of a DC to DC buck boost converter connected to rectified AC line. यह आपकी rectified AC line है. This is the single phase bridge rectifier which is connected to source, AC source. This is source voltage Vs. और ये आपका line filter है. This is line filter. This is source current Is, and this is IL. आपका switch, inductor L, and you have a diode like this. Right, this is capacitor, output capacitor, and this is load. आपकी load voltage अब negative है, plus minus V0, and load current भी obviously negative है, because in a buck boost converter, why is it called buck boost converter? Because average output voltage is greater than or less than peak input voltage. When it operates as a buck converter, average output voltage is less than peak input voltage. But when it operates as a boost converter, the average output voltage is greater than peak input voltage. The question is, when will this operate as a buck converter? When duty ratio of this switch is less than 0.5, and when duty ratio is greater than 0.5, then it will operate as a boost converter. So you can operate this AC to DC converter as a buck converter or as a boost converter depending upon the duty ratio. Now, यह आपकी पहली पल्स है जिसके दौरान आपका स्विच ऑन है और इस दौरान स्विच ऑफ है. फिर आपका स्विच फिर से ऑन होता है फिर ऑफ होता है एंड सो ऑन। तो पहली करंट पल्स आई एस आपकी यहाँ से यहाँ, व्हेन द स्विच इज ऑन करंट फ्लोज लाइक दिस, और इंडक्टर आपका चार्ज हो जाता है और इंडक्टर करंट बढ़ जाता है। और जब स्विच ऑफ हो जाता है, व्हाट इज दिस करंट, क्योंकि स्विच आपका ऑफ हो गया है, एकदम अब्रप्टली जीरो हो जाती है। तो यहाँ स्लोली जीरो नहीं हो जाती है, वो दैट वाज हैपनिंग इन बूस्ट कन्वर्टर, बिकॉज हियर व्हेन स्विच इज ओपनड, so there is no path for the current IL to flow, so it becomes zero, although load में current flow हो जाएगी लेकिन सोर्स से कोई current नहीं आएगी, so there is no D1 खत्म हो गया। one current pulse, this is next current pulse। So therefore if this is your source voltage without filter, आपकी source current ऐसे होगी। Negative half cycle maybe, okay, this is your source, and with filter ये perfectly sinusoidal हो जाएगी। Let me show you those waveforms। This is VS source voltage, source current, इनके relationship मैं आपको दिखाऊंगा अभी थोड़ी देर में, source voltage, source current, और ये आपकी ओमेगा टी एक्सिस है और ये source voltage waveform है VS, और यहाँ से मैं आपको with respect to ओमेगा टी source current दिखाऊंगा। First of all the relationship between source voltage और source current, उसके लिए मुझे IL average की एक्सप्रेशन लिखनी पड़ेगी। ये IL average जो यहाँ आती है, this is VL and this is IL, and this is given by this equation, it is given by D square TS by 2L into VLT। इसमें there is no D1 term because D1 is absent here। When the switch is opened, current abruptly falls and it gives a better shape to the current, and whatever non-linearity in the relationship between VS and IS was there in the boost converter, that non-linearity is over, वो खत्म हो जाती है, और आपकी the relationship between source voltage and source current is perfectly linear। You see, it is a straight line in positive half cycle as well as in negative half cycle। So therefore आपकी source voltage perfectly sinusoidal हो जाती है, ये देखिए। So therefore if you draw one cycle of source voltage 0 pi 2 pi like this, and you draw one cycle of source current after you insert filter here, a small high pass filter which will remove all the high frequency harmonics, so आपकी source current in presence of filter perfectly sinusoidal हो जाएगी and in phase with the voltage। So therefore your AC to DC buck boost converter will act as a perfectly linear load, because source voltage is sinusoidal, source current is also sinusoidal, so no harmonics injection will be there, and the input power factor is unity 1.0, so that means no reactive power is drawn by the converter। So therefore this AC to DC buck boost converter removes the non-linearity in the boost converter and it makes the source current perfectly sinusoidal, so it is an excellent candidate, it's an excellent candidate for self PFC, self power factor correction। but लेकिन इसमें buck boost converter में एक problem है, and problem is that there is no common ground between input and output। फॉर एग्जाम्पल अगर ये इनपुट है आपकी AC, इसका न्यूट्रल ये है, आई मीन रेफरेंस पॉइंट ये है, लेकिन इसमें दिस टर्मिनल इज पॉजिटिव, दिस इज नेगेटिव, इसमें रेफरेंस पॉइंट ये है, द टू रेफरेंस पॉइंट्स आर डिफरेंट, इन अदर वर्ड्स इट गिव्स नेगेटिव आउटपुट वोल्टेजेस, and in those applications where you need positive voltage, say plus 5 volts regulated voltage or plus 12 volts or plus 20 volts, you cannot use this buck boost converter because it gives negative output voltage। You can see very clearly it gives negative output voltage। So how to overcome this problem? Otherwise it was a best candidate for self PFC। To overcome this problem, we have another type of AC to DC improved power quality converter, which is called AC to DC flyback converter। Flyback converter, let me quickly show you the power circuit diagram of AC to DC flyback converter। This is source voltage, AC source voltage, This is your line filter, which is passive LC filter, high pass filter, small sized filter. This is source current IS. और इसके बाद आपका दिस इज IL, या आपकी VL है, और आपका फ्लाईबैक कन्वर्टर आ जाएगा. और फ्लाईबैक कन्वर्टर लुक्स लाइक दिस. You must already remember, you must be knowing how does a flyback converter look like. मैग्नेटाइजिंग इंडक्टेंस है LM, ये प्राइमरी वाइंडिंग है ट्रांसफार्मर की विद मैग्नेटाइजिंग इंडक्टेंस LM, and that this is a high frequency transformer. Secondary is here. This is load, and load voltage is V0. This is a high frequency transformer. अगर आपका स्विच से 10 किलोहर्ट्ज पे आप इस कन्वर्टर को ऑपरेट करते हो, सो यू हैव टू डिजाइन योर ट्रांसफार्मर एट अ फ्रीक्वेंसी ऑफ 10 किलोहर्ट्ज. उस पे साइज ऑफ ट्रांसफार्मर विल बी वेरी वेरी स्मॉल. नाउ व्हेन द स्विच इज क्लोज्ड, करंट फ्लोज इन द प्राइमरी वाइंडिंग लाइक दिस. ये पॉजिटिव हो जाता है, सेकेंडरी में ये पॉजिटिव हो जाता है, ये नेगेटिव. सो देयर इज नो करंट ड्रॉन बाय द सेकेंडरी वाइंडिंग, क्योंकि इसमें ये पॉजिटिव हो जाता है, डायोड रिवर्स बायस हो जाता है. एट दैट टाइम कैपेसिटर इज ऑलरेडी एनर्जाइज्ड, इट सप्लाइज पावर टू द लोड. एंड व्हेन दिस स्विच इज ओपनड, व्हाट हैपेंस? व्हेन द स्विच इज ओपनड, ये करंट यहाँ जीरो हो जाएगी. सो यू आर ब्रेकिंग एन इंडक्टिव पाथ. लेकिन जो मैग्नेटिक फील्ड जो इसको सेकेंडरी के साथ लिंक करता है, all the energy which was stored in the primary winding of the transformer, it shifts that energy to the secondary side, और पोलैरिटी ऑफ वोल्टेज चेंज हो जाती है, जिससे ये डायोड फॉरवर्ड बायस हो जाता है. और ये जो एनर्जी है, इट इज दैट एनर्जी फ्लोज इनटू द आउटपुट स्टेज. पार्ट ऑफ दैट एनर्जी चार्जेस द कैपेसिटर एंड अदर पार्ट ऑफ दैट एनर्जी गोज टू द लोड. ओके, तो ये इस तरह सिचुएशन है. So this is switch on, here switch is off, then it is again on, and so on. और आपकी सोर्स करंट ऐसे है. When switch is on, the IL flows, और आपकी सोर्स करंट हाई हो जाती है. And when switch is off, सोर्स से कोई करंट फ्लो नहीं होती, although लोड में करंट फ्लो. प्राइमरी साइड में करंट जीरो हो जाती है, सेकेंडरी साइड में फ्लो होती है. I am not going into the details. I hope and I presume that you already know the operation of flyback converter. When second control pulse comes, again current in the primary winding flows, but no current in the secondary winding. But a high current will flow in the primary winding, and when switch is off, there is current in the secondary winding, not in the primary winding. This is the only transformer operation where you will see that current at one time is flowing either in primary winding or secondary, not simultaneously. Otherwise, transformer में आपने पढ़ा है transformer operation में, when current is flowing in the primary winding, same time current is flowing in the secondary winding also. But in this flyback converter, at one time current is flowing in only one winding. When switch is closed, current flows in the primary winding, and because of reverse bias across this diode, there is no current in the secondary winding. And when switch is opened, there is no current in the primary winding, and at that time current is flowing in the secondary winding. Anyway, the average DC line current is given by same equation. It is given by D squared TS by 2L into VLT. और इसमें अगर आप देखेंगे ये relationship between source voltage and source current, and this is omega T versus source current. और आपकी सोर्स वोल्टेज फॉर एग्जांपल ये है ओमेगा टी एंड सोर्स वोल्टेज, ये सोर्स वोल्टेज है प्योरली साइनोसॉइडल. द रिलेशनशिप बिटवीन सोर्स वोल्टेज एंड सोर्स करंट, जस्ट लाइक बक बूस्ट कन्वर्टर, इज परफेक्टली लीनियर, which gives purely sinusoidal source current. So therefore, if this is one cycle of source voltage, the source current will be perfectly sinusoidal in presence of filter and in phase with the voltage, giving unity power factor operation. And your AC to DC flyback converter looks like a linear load to your source. No harmonics in the source current, no reactive power delivered to the converter. So therefore, just like buck boost converter, this flyback converter also is an excellent candidate for self PFC, self power factor correction. And it is one of the best improved power quality AC to DC converters, one of the best IPQCs. And output voltage is positive. Buck boost converter में क्या problem थी? Output voltage was negative. And one extra advantage which is not there with the buck boost converter or with other DC to DC converters is that this high frequency transformer, whose size is very, very small, it provides electrical isolation between output stage and input stage, and which is one of the requirements in switch mode power supplies. Switch mode power supplies में एक requirement ये भी है that output stage and input stage should be electrically isolated, and that electrical isolation is elegantly provided, very easily provided by this isolation transformer, high frequency isolation transformer. So therefore, AC to DC flyback converter offers all the advantages of AC to DC buck boost converter, gives excellent self PFC property. In addition, it provides electrical isolation between output stage and input stage and gives positive variable DC output voltage or positive regulated DC output voltage. Okay, so therefore it is one of the best AC to DC improved power quality converters for power factor correction. And then I will discuss with you AC to DC forward converter. Forward converter. And this AC to DC forward converter looks like this. Let me draw the power circuit diagram, then I will explain a little bit. This is source voltage, line filter, source current, and your this forward converter looks like this. This is the switch. And then this is the secondary winding. This is load voltage V0 plus minus load current is I0. Problem flyback converter, forward converter में ये है, when you are closing the switch, there is current flowing in the primary winding and simultaneously there is current flowing in the secondary winding also. No problem, it's okay. But when you are opening the switch here, जब ये switch आप open करते हो, आप inductive current basically break करते हो. There is no current in the primary winding and at that time there is no current in the secondary winding also. That means you are breaking an inductive circuit. If you are breaking an inductive circuit, then your switch will, there will be high voltage spike and the switch will immediately get damaged. To prevent that damage, when you are opening the switch, जो भी इसमें एनर्जी है, वो एनर्जी उसके लिए उसको आप एक पाथ देना है. आपको ये वाइंडिंग ट्रांसफार्मर की डीमैग्नेटाइज करनी है. उसके लिए आप एक टर्शियरी वाइंडिंग, तीसरी वाइंडिंग यूज करते हो ताकि ये एनर्जी जो इस इंडक्टर में थी वो यहाँ से ऐसे डिस्चार्ज हो जाए एंड यू विल नॉट बी ब्रेकिंग द इंडक्टिव पाथ. लेकिन उस वक्त करंट इसमें ये वाइंडिंग जो है जो इसको डीमैग्नेटाइज करेगी, ये इसमें करंट ऐसे फ्लो होनी चाहिए. बट प्रॉब्लम हियर इज दैट this is a rectifier. This rectifier blocks the flow of this current. अगर ये DC to DC converter होता सिंपल, यहाँ DC सोर्स होती तो ये करंट फ्लो हो जाती, नो प्रॉब्लम, और ये वाइंडिंग को डीमैग्नेटाइज करता और स्पार्क it would not have damaged this switch due to high voltage spike. But because this current, demagnetizing current, has no path, because this rectifier will block this current, so therefore it has no path और immediately आपका switch high voltage spike की वजह से damage हो जाएगा. Therefore AC to DC forward converter does not exist. I mean, because of this problem, we don't go for AC to DC forward converter. Okay, so therefore it is not suited at all for self PFC property. You cannot actually use it. Similarly, you have other types like SEPIC other types of AC to DC, these DC to DC buck, these converters which give AC to DC Chook converter, SEPIC converter, and Zeta converters. They are also not good candidates for self PFC क्योंकि वो इस टाइप की सोर्स करंट दे रहे हैं, which is not sinusoidal at all. ये देखिए वो इस टाइप की सोर्स करंट दे रहे हैं. It's not sinusoidal. So not good candidates. They are not good candidates for self PFC. Therefore, studying various types of DC to DC converters when they are connected to rectified AC line, we have studied various types of AC to DC improved power quality converters like AC to DC buck converter, AC to DC boost converter, AC to DC buck boost converter, AC to DC flyback converter, AC to DC forward converter, and AC to DC SEPIC, Zeta, and Chook converters. Let us summarize their self PFC properties. एक टेबल में मैं summarize करूँगा. First of all, I will write basic converter which is used in these AC to DC improved power quality converters. उनकी line current waveform भी हम draw करेंगे. Line current waveform. Second column. Third is discontinuous conduction mode self PFC property, self power factor correction property. And fourth is power level. आप कितने power levels तक कौन सा converter use कर सकते हो. First that we study today is AC to DC buck converter. And you have seen its line current waveform was like this. Some discontinuity was there near the zero crossings. This was line current waveform. So it was its DCM self PFC property is poor. It's not a good candidate. And power level is, you can use it, even if you have to use it, you can use it from low to medium power levels. That is about buck converter. Second type of AC to DC converter that we study today is AC to DC boost converter, जिसकी line current waveform कुछ ऐसे थी. Although it did not have these discontinuous periods, but it is slightly non-linear. Okay, so iski self PFC property we cannot say excellent, but it is good. It is better than that of AC to DC buck converter. Or iski power level is low to medium hai. We can use it from low to medium power levels. Third is buck boost converter. Buck boost converter. Its line current waveform is excellent, purely sinusoidal, in presence of filter, of course. And its DCM self PFC is excellent. और इसकी power level भी low to medium, लेकिन इसके साथ मैंने problem बताई, it gives negative output voltage. That's why its application is limited. Next is flyback, AC to DC flyback converter. It also gives purely sinusoidal line current in presence of a small high pass filter, and its DCM self PFC property is also excellent, but its power level is low. You cannot use it even for medium power applications. You can use it for low power application. Then forward converter. AC to DC forward converter. I will not draw its waveform because we cannot use it. I've already told you why you cannot use it. No. And finally, AC to DC Chook, SEPIC, and Zeta converters. इन तीनों AC to DC converters की waveform non-sinusoidal है ऐसी. ये एकदम ड्रॉप हो जाती है, साइनोसॉइडली ड्रॉप नहीं हो जाती है. ये देखिए एकदम ड्रॉप हो जाती है. So poor self PFC property and power level is low to medium. Therefore, out of these, buck boost converter has good self PFC property. Wherever you can use it, you can use it. But if you want excellent self PFC property, then you have to make a choice between buck converter and buck boost converter and flyback converter. If your output voltage, I mean you need a negative output voltage, then buck boost converter is best. But if you need positive output voltage, then flyback converter is having excellent self-PFC property. So therefore, in today's lecture, we have discussed various types of improved power quality AC to DC converters. First of all, I told you what are the serious drawbacks of conventional or traditional AC to DC converters, and what are improved power quality converters. I mean, there are problems with passive filtering, active power filtering. Then we can go for improved power quality converters. What's an improved power quality converter? And I told you that when DC to DC converters are operating in discontinuous conduction mode and they are connected to a rectified AC line, they give self-PFC property. They act as improved power quality AC to DC converters. And we have studied various types of improved power quality AC to DC converters like AC to DC buck converter, AC to DC boost converter, AC to DC buck boost converter, AC to DC flyback converter, AC to DC forward converter, AC to DC choke, SEPIC and zeta converters. And we have studied their waveforms, line current waveforms, and their self-PFC properties. And it will be very easy for you to decide which type of AC to DC improved power quality converter you can use in a particular application. But when you are designing the control algorithm for these AC to DC improved power quality converters, you have to ensure that they have to operate in discontinuous conduction mode of operation. And in discontinuous conduction mode of operation only they will give improved power quality at input side, that's self-PFC property. If you try to operate them in continuous conduction mode, then they will lose self-PFC property. Operating them in continuous conduction mode, then you have to use a different strategy. I will discuss that inshallah in next lecture. The reference which I have, the research paper from which I have studied this various types of improved power quality AC to DC converters operating in discontinuous conduction mode. This is the reference. You can also download this research paper. The title of the research paper is Comparison of Basic Converter Topologies. Comparison of Basic Converter Topologies for Power Factor Correction. This is the, अगर आप ये Google पे भी डालोगे, if it is available there, you can get it from there. Otherwise, in our institute we have got subscription of IEEE. You can download it from there. The authors are Huai Wei and Isa Batarseh. This paper was published in 1998 in IEEE conference. This is the reference for you. Okay, so with this I will end my today's lecture. All the best to all of you. Thank you.